All right, this is the class starter from Friday that we started on after your test on Friday. And we did 1 and 2, and in both of those, what we did was we followed the same sequence of steps. We factored, and then we looked, before we did any kind of simplification, we identified the domain. And because we're dealing with rational expressions, they're going to have denominators. And we know whenever we have a denominator, we got to ensure that it's not equal to 0. So we did, after factoring, we identified any values of x that would cause us to get a 0 in the domain, or 0 in the denominator, and then excluded that from the domain. And then once we factored and identified domain, then we were able to cancel any like factors to simplify our expression. So we did that in 1 and 2. And so for number 3, for number 3, we're going to do the same steps. So to factor that numerator, what do we need to do?
You need to group and you need to do that.
All right, so in the numerator, we're going to group. Since there's 4 terms, we're going to be careful about that minus and make it plus and negative 80x, and then group those 2 terms together. And so, what are we going to take out from the first grouping? 9x squared. And that's going to leave us with 5x minus 7. Good. And then what's from the second grouping are we going to take out? And hopefully that's going to leave us with 5x minus 7 as well. All right, so we know that grouping is going to work because what's left over, 5x minus 7, can be factored out momentarily. But in the denominator, we're dealing with a trinomial. And so how do we go about factoring that? We could rewrite it as negative 15x squared plus x plus 28. And then we need 2 numbers that multiply to whatever negative 15 times 28 is. And then 2 numbers that multiply to that and then add to 1. And I think the 20 needs to be negative. Okay. And then we'll do negative 15 over each of those. So negative 15 over negative 20 would reduce to 3/4. And negative 15 over 21 would reduce to negative 5 over 7. 5x over 7. Because when we do negative 15 over negative 20, the negatives cancel out. So it just becomes 15 over 20, which would be 3 over 4. And then negative 15 over 21, we produce a negative 5 over 7. And then we'll keep going. We'll factor out the 5x minus 7 from the numerator. That's going to leave me with 9x squared minus 16. And in my denominator, I'm really kind of done factoring. Although, if I'm looking ahead, what would I need to do with this negative 5x plus 7? Right, I'm going to take the negative out because that's going to give me 5x minus 7, and that's going to eventually factor with the 5x minus 7 in the numerator. So I kind of want to look ahead for those kinds of things. And of course, the 9x squared minus 16 is the difference of 2 perfect squares. So completely factored, this is 5x minus 7, 3x minus 4, and 3x plus 4. And then in my denominator, I have a negative 3x plus 4 and a 5x minus 7. Okay, so we've completely factored that expression. And we notice there's going to be things that are going to cancel out, but before we carry on with that, we want to identify our domain. And we can do that either in set builder or in interval notation. So in set builder notation, tell me what x cannot be.
Negative 4/3.
Negative 4/3.
7/5.
Or positive 7/5. Those 2 values will cause me to get a 0 in the denominator. We could write it in interval notation, which would be from negative infinity to negative 4/3. And then negative 4/3 to 7/5. and then 7/5 to positive infinity. Either one of those will be acceptable for a domain. And once we've identified the domain, then we're ready to simplify. What cancels?
3x plus 1.
And all that's left is going to be a negative 3x minus 1.
So you could just write negative 3x plus 1.
Yep, you could do negative 3x plus 1. Good. All right. Probably good on number 3. All right, 4 and 5 really related to our last unit on polynomials, but never hurts to go back and review, because a lot of these terms and skills that we saw in polynomials are going to carry forward into rational functions, because a rational function really is a polynomial divided by a polynomial. So, keeping our skills fresh in polynomials will be important. It says, given this function, where y equals negative 2 times the quantity x plus 3 squared times x minus 2 cubed, I want to classify the points at x equals negative 3 and x equals 2. And when I say classify, I just simply mean, name them, describe them, anything that you would know about the points at each of those x values. Any thoughts?
They're both zeros.
All right, good. We can say that they are both zeros of the polynomial because it causes us to get a 0 for y. Anything else that you want to say to describe those? Try to be as specific as we possibly can.
X-intercept.
All right, they're x-intercepts.
There.
Multiplicity.
All right, there is a multiplicity. What's the multiplicity for 2? All right, so it's a 0 or an x-intercept with a multiplicity of 3. And at negative 3, it's got a multiplicity of what? Okay. So what does that mean? One's going to be parabolic. At x equals negative 3, the graph's going to appear to be parabolic at that point. And at x equals 2, the graph's going to appear to be cubic at that point, which means that we can even further describe those points. What does it look like at that point where the graph appears to be cubic, or what is it called? And this graphically, it looks like this. And what is that point called? Told you that name before.
The point of inflection.
Good. This is actually going to be a point of inflection. Anytime the graph looks like a cubic function at a particular point, or takes on that cubic shape at a point, that point's known as a point of inflection. You're going to learn a lot more about that in calculus. It really tells you something significant about a particular scenario whenever you're dealing with a point of inflection, because there's a change in concavity. It's called, the graph changes from concave down, which would look something like this, to concave up, which would look something like that. So it's kind of cupped downward would be concave down, and then cupped upward would be a concave up. And so when it changes concavity, then that's known as a point of inflection. Like I said, you'll learn a lot more about that in calculus. What about here at negative 3? We've already said the graph's going to look parabolic.
Would it be a relative maximum? Because
Well, it would definitely be a relative extrema. Okay, so it could be, it's going to be either a relative maximum or a relative minimum, because we know at that graph, or at negative 3, it is going to take on that parabolic shape. So
It's got to be
either like that or like that.
doesn't it have to be a relative maximum, since it's a negative a.
All right, we could, based on the end behavior, probably make a better conclusion about what kind of extreme value it is. What's the degree? Odd, so that means that the end behavior goes in opposite directions. And what would the leading coefficient be? Negative. So considering the end behavior with odd and a negative leading coefficient, I believe the end behavior is going to look like this. which means that at -3, the graph's going to be going upward. So what kind of extreme value do we have at -3? And we actually have a minimum there. And we would say a relative minimum because I know over here at 2, the graph's going to point downward. So that's not going to be the smallest y value on the graph, but it is going to be a relative minimum because the graph does bounce off the x-axis right there. And so therefore we have a minimum. And that end behavior really was very helpful in determining. All right, good. So we were able to describe them as zeros, but we really could take it even further by recognizing their multiplicity and then using that multiplicity to get us a better idea of what the graph looked like. Combine that with things like end behavior and get a real clear description of what's exactly happening in each of those zeros beyond just them being x-intercepts. All right, and then number 5, I think you had a problem like this on your take-home, if I'm not mistaken. Says profit is determined by multiplying the price of a unit times the number of units sold minus the cost of producing the number of units. Okay, so there's a whole lot that's embedded in that statement. But if you wanted to take this first sentence and translate it into a mathematical equation, how could you write that? Yeah, P equals P being the profit, right? So profit is determined by, so profit equals by multiplying the price of a unit times the number of units sold. So what do you want to, we'll say maybe D can be the price and X could be the number of units. So how do we translate the price of a unit times the number of units sold? D times X minus the cost of producing the number of units. So our equation would look something like this. The profit is determined by taking whatever the price is, multiplying it by the number of units sold, that's the revenue. So if I'm selling some unit for $5, I'm going to say $5 times however many of those that I sold, and that's going to give me my revenue. And then I'm going to subtract from that the cost of producing those, and that's going to tell me how, my profit, how far ahead I am in this scenario. So if the price of each unit X is given by, they actually use lowercase p to represent price. So if I wanted to change that, and this is a lowercase p for the price. We use uppercase P for the profit. So if the price of each unit is given by P equals 130 plus 0.2x squared, and the cost of producing X units is given by C, which is 75x plus 2,000, find the break-even point. So we'll start plugging everything in. Profit is equal to, what's the expression for the price?
130.
That's lowercase p times x minus the cost function, which is 75x plus 2,000. And so we can simplify that polynomial expression. The profit's going to equal 0.2x cubed. This is 130x minus 75x, which is plus 55x minus 2,000. So there's our profit function. That really gives us the revenue minus the cost. And we want the break-even point. In other words, the number of units that must be sold to get a profit of 0. So we're going to plug in 0 for P, for big P. how you want to solve that equation.
Calculator.
Yeah, calculator, I think. So we're going to plug that into y equals. Of course, we'll adjust the window as need be until we can find the x-coordinate where the graph crosses the x-axis, which is the 0 of the polynomial. There might be multiple answers, but I think we would want the first one, where it's the first time that we're going to break even. That's going to tell us how many units we would have to produce and then sell to break even, and then from that point forward, start making a profit. 17.3. So we can say approximately 17 units. Because once we sell the 18th unit, then now we're going to be on the positive end of that. Start making money. Okay, everybody good? All right. So as I said, we are going to move forward with performing operations on our rational expressions. And ultimately what we're going to work towards is not only being able to simplify these rational expressions, but also to solve equations that involve these rational expressions. If you remember, I said that really the goal of pre-calculus is to be able to solve everything and graph everything. So by the end of the week, you're going to be able to solve rational equations. That's just another type of equation that you might encounter that you would need to solve. And we're going to even see some good application problems of solving rational equations. And then towards next week, we're going to actually, with our EQT next week, we're also going to focus in on graphing rational functions. So again, we're kind of on that trajectory of being able to solve every kind of equation and graph every kind of function. But before we get to the solving, then we've got to do some simplifying. And we have to be able to work with different operations like addition, subtraction, multiplication, and division on our rational expressions or fractional expressions. A rational expression is just a fraction. We talked about that on Friday. So we're going to work with simplifying them and ultimately work towards being able to solve those kinds of equations. So this just kind of puts some notes to what we were doing on Friday. We said this, that a rational expression is a fraction that has a polynomial of a numerator and denominator. So now we're dealing with fractions where there's going to be variables in the numerator and denominator. And part of the process of working with those is we want to be able to simplify those expressions. It's going to make it a lot easier to solve equations, and it's going to make it a lot easier to graph functions if we can take a complicated expression and then simplify it in some way by canceling like factors. And of course, as we talked about on the class started today and on Friday, part of this process, particularly since we're going to eventually work towards graphing these, is being able to identify the domain. That domain, since we're dealing with fractions, is going to be whatever causes us to not get a 0 in the denominator, so we want to make sure that we consider that.
I don't know if they sent out or not, but that's what they sent to us. Just like
And so it says, when we've talked about domain in the past, that of course we've said that there's two issues with domain. There's denominators and there's square roots. And dealing with rational expressions, we know we're going to end up with denominators, and so we're going to identify any time that we might get a 0 in the denominator as something that would be excluded from our domain. And we saw this on Friday. We factored, and then we identified the domain, and then we simplified. And you always want to identify the domain before you do any simplifying, because we're finding the domain of the original expression. So I can't cancel anything. I've got to find the domain first, and then I can do my canceling after that domain has been identified. So you probably don't even need to really write this down, because this is what we were doing in class on Friday and this morning. We're going to simplify by factoring and canceling. And of course, finding the domain is going to be part of that, in between the factoring and the canceling. On Friday and this morning, we just dealt with one single expression. It's one fraction. But we can multiply fractions together or divide fractions. We know that really kind of cross-canceling is the key to multiplying and dividing fractions, and that's still going to be true when we multiply and divide rational expressions. What's the only thing you have to remember about dividing fractions? How do we divide fractions? Yeah, we multiply by the reciprocal. So if we have two fractions that we're dividing, we're going to copy the first fraction down, change it to multiplication, and then do the reciprocal of the second fraction. Okay? And we'll just go through some simple examples of this. An example or two of adding and subtracting. So let's look at number 2. We want to simplify this, and you notice this is a multiplication problem. And what are we going to have to do before we do anything when we go simplify this?
First the domain.
Well, before we can find domain, what do we have to do? Now, factor. Yeah, we got to factor first, and that's going to help us identify domain, and then it's also going to show us any like factors that we're going to be able to cancel. So this is pretty easy to factor. We'll factor the numerator, and it factors into x plus 4 and x plus 3. We'll factor the denominator, and it factors into x plus 2 and x plus 1. Factor the numerator here, and that will be x plus 3 and x plus 2. And then the denominator would factor as x plus 3 and x plus 3. Trust you can do that on your end without a problem. So just like when we were working with one expression, when we're multiplying and dividing, we're going to factor first, then we're going to identify domain. So let's do that at this point. Tell me all the values that x cannot do.
-2, -1.
Okay, so our domain is all the x's such that x is not -2, -1, or -3. We could write that in interval notation if you wanted to. -infinity to -3, then -3 to -2, then -2 to -1, then -1 to positive infinity. But set builder in this case is probably a little bit more efficient way of doing so. And then we factor, we domain, and then we cancel. And what all is going to cancel here?
Everything except for x plus 1.
All right, this x plus 3 can cancel with one of those. And then with multiplication, we can cross cancel. So this x plus 3 cancels with this one. And this x plus 2 cancels with that one. And so all that's left is x plus 4 on top and x plus 1 on bottom. So you can see we've got to do domain before we cancel, because otherwise we would think that our domain would just be x can't be -1. But we're really finding the domain of the original expression, which would include -2 and -3. All right, you try number, the one that's down here listed as number 3. All right, so we'll factor this. The numerator is difference of perfect squares. That's 2y minus 3 and 2y plus 3. The denominator is a quadratic trinomial that factors. What does it factor it to? 2y minus 3 and y plus 6. Then we're multiplying, and the other fraction will factor the numerator quadratic trinomial, so that's going to factor into 2y plus 3 and y minus 2. And then the bottom one would be y plus 6 and y minus 1.
That's bottom minus 1 all
All right, so we have factored everything. Of course, before we do any canceling, we have to find the domain. And what can x not be? 3 halves, negative 6, and 1.
No, yeah, that's true.
That's it? Okay. And then now we're ready to start canceling anything that will cancel. So the 2y minus 3's will cancel, one's the numerator, one's the denominator. The y minus 1's will cancel. And that's it. So what we're left with is 2y plus 3 squared over y plus 6 squared. That would be our simplified expression.
So you don't have to.
No, I would. I take that in that factor form. And dividing, if we can multiply, dividing is really easy because all we're going to do is to remember that we're going to multiply by the reciprocal of the second fraction. So let's say here we'll do this one. The first thing I'm going to do is factor, of course. So the numerator we'll factor is a plus 5 over 8, or times a plus 2. This would be a minus 6. And then you notice it's division. But what so I'll go ahead and factor this, but I know that what I'm going to do in solving is actually multiply by the reciprocal. But you got to be careful with the domain of division problems, because you want to start by identifying the domain before you flip and then again after. Right? So for example here, tell me before I multiply by the reciprocal, what can x not be? 6 and negative 6. I'm going to leave that open because now when I flip this over, I'm going to multiply by the reciprocal. Now you'll notice that a plus 5, that was not in a denominator, now it is. So what else has to be excluded from our domain? Negative 5. So you got to be careful with the division problems to ensure that you identify the domain before you flip and again after in case anything is added to that domain. And now let's see, it's multiplication, so we can start canceling. The a plus 5s will cross cancel, the a minus 6s will cross cancel, and all that's left is a plus 2 times a plus 6. We'll do one more.
We do the one.
We're going to do that here. This one's written differently, but it's still a division problem. I mean, when we have a fraction bar like this, that still means division. So if it helps, just rewrite it as the way we would traditionally write the division, or the division of two fractions. Yep. So now, why don't you try that? I'll give you a minute or two. So factor it now that we've written it as a traditional quotient problem. Factoring that first numerator be 2x plus 1 and x minus 2. And the denominator is the difference of two perfect squares, so x minus 1 and x plus 1. And divided by 2x plus 1 and x plus 2. And in that denominator, that would be x plus 2 and x minus 1. So there's our factored form of that quotient. Let's go ahead and identify the domain before we do anything else. X cannot be, all the x's such that x cannot be, all right, but I'm going to leave it open since it's a division problem in case I need to add anything after I've flipped over. So I'm going to have 2x plus 1 times x minus 2 over x minus 1, x plus 1. And then I'm going to multiply by the reciprocals. The x plus 2 and the x minus 1 move up. And the 2x plus 1 and the x plus 2 move down. Is there anything that we need to add to that domain? Yeah, negative 1/2 now. Because once we move that 2x plus 1 down to the denominator, then that means that now we have negative 1/2 as a restricted value that would give us a 0 in the denominator. So we factored, we've switched this to a multiplication, we've identified the domain along the way, and so now we're ready to cancel anything that cross cancels. So looks like the 2x plus 1s will cancel, the x minus 1s will cancel, the x plus 2s will cancel, and so the simplified form would be x minus 2 over x plus 1. And so what we'll do tomorrow is we'll pick up with adding and subtracting rational expressions, and then also look at something that's called a compound fraction, which can be a little bit confusing, so we want to make sure we pay attention on that. It's a really important skill to be able to simplify those. Then Wednesday we will work on solving equations, and Thursday we'll look at some practical examples of that, and then we should have a quiz on Friday on rational expressions and equations. All right, so there's your plan for the week. This will be your homework tomorrow night. The Stewart book, I'm going to have to make copies of that for you, but I'm going to do that here momentarily, so if you want, I'll give you a copy of it. And you can go ahead and start on it. Sorry the date's not right, but you can start on that tonight, which you are able to do. There'll be a few that, adding and subtracting that we haven't gotten to just yet. But you can at least get a head start on this, and this will be due on Wednesday. We'll go over it on Wednesday.
So you're going to go ahead and make copies of that.